Welcome to solverfy.
In this problem, we have light shining through three separate materials, each with a different index of refraction, N1, N2, and N3. In this diagram, they show us two possible paths the light can take to transmit into the third material. Because these paths have different lengths, in general, the two transmitted rays, will be phase shifted one from the other. And they want us to find which thickness L will result in maximum intensity of the transmitted light, which means that these rays will completely constructively interfere. And there's multiple thicknesses that will satisfy this, and they want us to find the second smallest thickness that will result in constructive interference, or complete constructive interference. The information they give us is that the indices of refraction are N1 equals 1.4, N2 equals 1.46, and N3 equals 1.75. The vacuum wavelength of the light is 482 nanometers. So for complete constructive interference, this extra distance traveled by what's labeled here as ray 4 has to be some integer multiple of the wavelength. So the extra distance traveled is twice this thickness L, so that's 2L, must equal an integer multiple of the wavelength, but this is the vacuum wavelength that I've called lambda. And in this material, it's got some index of refraction, so the wavelength in the material is lambda over the index of refraction, which is N2. So that's the wavelength in the material, and we need some integer multiple of this, so we can just multiply by an integer, which I'm going to call m. So n is 1, 2, 3, 4, etc. Now, we have to account for any other possible phase shifts that occur. And when you go from a lower index of refraction to a higher index of refraction, the reflected ray will be phase shifted by half a wavelength. So we have to check for this. So the first reflection, we're going from N2 to N3, and that's a lower index of refraction to higher index of refraction. So that's an extra phase shift of half a wavelength that we have to add on to here. When we're going from N2 to N1 on the second reflection here, we're going from a higher to lower. So there's no phase shift here. So all we have to add is an extra phase shift of half a wavelength, or we can subtract it. It's the same thing. And I'm going to subtract instead of add. So now this equation is correct for constructive interference. And all we have to do is solve for L. So L now is going to be lambda over 2 N2 times m minus 1/2. And we want the second smallest thickness. Well, the smallest is if we set m to 1, that's the smallest this can be. So the next one is we set m to 2. So set m equals 2. So we're going to get L equals, well, 2 minus 1/2 is 3/2. So that's going to be 3 lambda over 2, but there's another 2 in the numerator here, so it's over 4 and 2. And all we have to do now is plug in the numbers that are given up here, and we find that the thickness is going to be 248 nanometers.